Welcome. This is Tumine Joshua, and I'm going to be taking you through inorganic chemistry. And today's topic is going to be halogens. I'm going to go through the trends of the periodic table of the halogens. Don't forget to subscribe to this YouTube channel and comment. And let's get your feedback so that we make improvements. So allow me to start. We are going to be looking at halogens, like I've already said, and okay, there we are. Group 7 elements are the so-called halogens, and we very well know that the halogens, they have a general electron configuration NS2, NS5, actually NP5. I think we have to correct that, NP5. So allow me look at that critically. There was some error here. NP5. Okay. Those are the trends that I want us to focus on today. We know very well that fluorine is a yellow gas. Chlorine is greenish yellow or pale green gas. Bromine is a red liquid. Then iodine is usually a purple solid or black, so depending on the conditions. The boiling point of fluorine is negative 188. The one for chlorine is negative 34. And the boiling point for bromine is 58. Then the one for iodine is 183. Bond energy. You can see everything is very clear. And we have 37, 57.2, 45.4, 35.6. Electron affinity, of course, that is the energy and it is usually exothermic. That's why it is having the minus. But that minus does not necessitate anything big. Just know it means that it's an exothermic energy. Electronegativity, you can see 4, 3, 2.8, 2.5, so it's decreasing down the group. And then we have electron potential. The electron potential, you can see, let me try to analyze everything. Yeah, you can see the electron potential is there, plus 2.87. And down the group, you can see that the plus is reducing. So meaning that the upper one is the most oxidizing, since the more positive you are, the more oxidizing you are. And the more negative you are, the more reducing you are. Now, you have to note that you see me not talking about the astatine. This astatine, the reason why I'm not talking about it is because it is a radioactive element. And these radioactive elements don't follow the same trends like for these other elements of, for example, group 7, I'm trying to talk about. To go on, let's talk about the boiling points. The boiling points, we know very well that we've seen it generally increasing down the group. And we're saying that the boiling point and the melting points of group 7, we have to think and see that the atomic molecules have simple molecular structure. They are simple molecules, you know very well, and they have those molecules held by the weak van der Waals forces, whose magnitude depend on the molecular mass of the molecule. So if the molecular mass is increasing, then we expect even the boiling point or the melting point to be increasing. So this is how you state the trend. We are saying that the boiling point increases generally down the group 7 elements. This is because the simple molecules are held by the weak van der Waals forces of attraction, and we are saying that whose magnitude increase with the increase in the magnitude of the molecular mass. So when the molecular mass increases, then even these van der Waals forces do what? Increase. Go on. So that is a simple graph showing the increase. Now, someone may ask, what did you base on? We know very well fluorine. Its molecular mass is lower than the one for chlorine, and even chlorine has a lower molecular mass than bromine, and even bromine has a lower molecular mass than iodine. So it means that the one which is having the highest molecular mass, that is to say iodine, will have higher boiling points and melting points. And you can see that the one for fluorine and chlorine, since for them they are gases, are already in negatives throughout. So it means that for you to have the melting point and the boiling points, you must first of all instead freeze them, because for them they are already gases at room temperature. So for that particular reason, you know what I'm trying to talk about right now. You can continue. Let's describe now the bond energy. You must have seen that the bond energy actually does what? Decreases. So this is the key word, decreases from chlorine down the group. Okay? And the reason is due increase in the atomic radius, which decreases. So the atomic radius decreases the what? The nuclear attraction for the bond pair. And this automatically increases the bond length. Okay? However, we must have noted so well that the bond energy of fluorine is lower than expected. So that is an anomaly. And when you're explaining these things, you must talk about the anomalies to be able to understand why fluorine is behaving differently. So we're saying that the bond energy of fluorine is lower than expected due to small radius, which makes the lone pairs of electrons easily approach each other. And therefore, there is further repulsion. And of course, when there is further repulsion, we expect increase in the bond length. Therefore, the bond energy does what? Decreases. So that's why it is having lower bond energy than expected. Go on. That's the thinking. I didn't want to rush this. We can still continue looking at every single thing. Sorry. Look at the one for fluorine. Now, look, bond enthalpy, first of all, is that particular energy required to break this particular bond, the covalent bond between those atoms, between the two atoms. So we see that the one for fluorine is lower than expected, but starting from chlorine, the general decrease is evident enough. So that is the general information. You give the general information, and then you give this as an anomaly. This is an anomaly. So the energy required to break this particular covalent bond between those two atoms of FF, CL, BR, or II is what we call the bond enthalpy, and it decreases generally down the group. Okay. Let's look at electron affinity. Down the group, electron affinity, we've agreed, decreases from chlorine in particular to iodine due to reduction in the nuclear attraction for the incoming electrons, caused by the addition of an extra shell. You know very well there is always an addition of an extra shell that is filled, and therefore, incoming electrons experience greater repulsion, hence less energy is evolved. So remember, electron affinity, the more the energy evolved, the easy an electron can be added to the shell. So we look at those which can easily actually absorb or take up electrons. For them, they will be producing so much energy. So that's the thinking. But still, before we forget, there is still another issue here, that electron affinity of fluorine is lower than expected. And the reason is because it has a small atomic radius, and it gives a high electron density. Because a small atomic radius means that everything is so close to the nucleus, and therefore we expect electron density to be high. Okay, and then there is extra repulsion of the incoming electrons. Therefore, we expect that particular energy or electron affinity of fluorine to be lower than expected. So for it is lower than expected. Okay, you can move on. So that's the thinking. Electron affinity of group 7 elements. We have fluorine, you can see where it is. We should be expecting it to be actually maybe around here, at least above chlorine, but it's not there. It is lower because of what we just said. It's having very small atomic radius and therefore high charge density. Because the electrons are so close to the nucleus, there is greater attraction. And because of that particular reason, we expect that the incoming group, incoming electrons will be repelled more. But the general trend, you can easily see how everything is decreasing generally. So those are the few trends. Don't forget to subscribe to this YouTube channel and comment. You like, comment, do everything, and let us improve our presentations. So allow me to stop here. The next time we're going to look at other trends, and we shall see how we can evolve. Maybe we look at electron negativities, we look at electron potentials, and many other things. Thank you very much.